Okay, so I'm going to talk to you about a MEMS-based magnetometer that we've been developing at the University of WA for remote sensing. Just for a bit of background, in terms of the ANFF node at the University of Western Australia and the capabilities that we have, one of the flagship capabilities relates to infrared sensing and imaging, and the other one relates to microelectromechanical systems. And the microelectromechanical systems work that we undertake at the university splits into two, one related to MEMS-based spectrometers, so tunable infrared spectrometers in the shortwave, midwave and long-wave infrared. We're basically infrared as far as sensing is concerned in that area. And the other area in terms of MEMS sensors and other MEMS devices, basically optical MEMS devices for atomic force microscopy readout, optical switching, and MEMS magnetometers. And these two, in terms of AFM readout and magnetometer, are based on a common platform, which I'll describe in a few minutes. But before that, what's the motivation here? Who's interested in magnetometers? Well, high precision vector magnetometers are of interest to a range of applications, especially airborne mineral exploration and undersea surveillance. A vector magnetometer basically is able to tell you not just the magnitude of the magnetic field, but also the direction. And you can do that by having sensors in a particular geometric configuration. So, and there's obvious, well not obvious, the main interest in airborne mineral exploration is that highly sensitive magnetometers are essentially measuring magnetic field anomalies, right? So a change in the Earth's magnetic field caused by something really, really big under the Earth's surface that can't be detected by other remote sensing technologies. So whether you use microwaves, infrared spectroscopy, etc., if it's buried, you ain't gonna see it. So magnetic field sensing, and companies like BHP and Rio Tinto do magnetic field surveys using very expensive aeroplanes flying super expensive squid magnetometers that have to be cooled down to liquid helium temperatures, etc., and it costs them tens of thousands of dollars an hour to run these things, whereas what they really want to do is just fly out a drone with something small and lightweight, etc. And it's fairly obvious what the interest is in terms of undersea surveillance, protecting bay areas or ports or etc., or not protecting, but essentially sensing in a network of sensors on the seabed anything that's big that passes overhead that changes the Earth's magnetic field. And I don't have to tell you what they are. So significant interest in defence and significant interest in the resource industry. I'm not going to go into too much detail about different technologies out there. Some of them are not suitable for vector magnetometers because basically they just give you a response that's independent of the direction. The technology that I'm going to describe measures the component of the magnetic field in a particular direction, which means that if you have three of them all orthogonal to each other, you can essentially resolve the full vector of the magnetic field. And some of them don't necessarily work too well within the Earth's magnetic field, which is about 65 microtesla. So some of them don't work necessarily in the Earth's magnetic field, some can't give you vector measurements, and some don't have the necessary sensitivity. So, I mean, MEMS magnetometers have been around, and it's all a question of how do I read the actual transducer? I can either do it capacitively, typically, where something moves and I measure it by changing capacitance, which is great because it's integrated, it's small, etc., but really not, sensitivity is better than around a microtesla. And other ones are optical techniques, but then similar to an atomic force microscope, I need bulk optics, and I'm not going to be able to put 100 of these distributed across the ocean floor as sensors, right? Forget it. So optical techniques give me super sensitivity, but they're really bulky, etc., take up a lot of room. electronic techniques based on capacitance measurements are great because they're integrated and small and lightweight, but they don't have the sensitivity. So effectively what we've done is come up with a technology that combines the advantages of optical readout in terms of sensitivity and the size, weight and power advantages of an integrated readout technique. So going to go back to first year physics, very simple situation here, a Lorentz force magnetometer. So you imagine you have a current sitting in flowing in a certain direction, magnetic field at some angle to that, whatever, then what that'll do is it'll cause a displacement of the beam orthogonal to the magnetic field and to the current flow. So if I can measure that displacement, I have a magnetic field sensor because that by measuring the displacement I can extract the force, and the force of course is directly related to the magnetic field and the current. So as I've said, traditional magnetometers based on the Lorentz force suffer from either being high sensitivity optical but bulky, or integrated and measuring very small deflection. But they don't have anywhere near the sensitivity required for what people want in terms of the airborne remote sensing for minerals, or whether they're looking for submarines or whatever from the ocean floor, is around typical numbers around 10 picotesla of sensitivity per root hertz. So how can we combine the two? Well, we combine the two with in a technology called LumiMEMS, which we have actually patented and has been applied already to an AFM. So one of our PhD students actually built an AFM out of it. So if you imagine you've got a waveguide, light coming in, light going out, and then you put a grating somewhere along there. You something is suspended above that, and the waveguide is designed such that at the wavelength of the light, it comes in and is scattered out by the waveguide. It's a grating out of the waveguide by the grating, and forms a resonant cavity between the underside of something and the waveguide. And depending on that separation, the light comes out the other end or does not come out the other end, or somewhere in between. So all I'm really sensing is the output power of light here, and that has a direct relationship to this separation between these two elements. So in a sense, it's a position sensor, right? And if you make one of these things and do it appropriately, you get regions where there's a nice linear relationship between the output power, the ratio of the output power to the input power, and this deflection, okay? Because it's basically just a resonant optical cavity. And that sensitivity is such that we can actually have demonstrated experimentally sensitivities of 2 picometers per root hertz readout deflection noise density, which is essentially like a signal to noise ratio if you want. So in other words, we can resolve movements in that top membrane of 2 picometers. And that translates to around about a sensitivity of about 20 picotesla per root hertz if you had a single double clamped beam structure, right? This beam structure where it's clamped at both ends, pass a current and measure how much it deflects. Given the deflection sensitivity, the magnetic field sensitivity is around 20 picotesla. Now that of course is not optimized. You could easily come up with a MEMS structure where you could have a current loop, etc. At every loop will multiply the sensitivity by another factor. So obviously it can be dramatically improved upon. In theory, this could even go up another few orders of magnitude, but we haven't tried yet, but that's basically what's being demonstrated experimentally. And this can be achieved, I should have mentioned that on that previous plot, that sensitivity applies across the whole range within the Earth's magnetic field. it's not up to 65 microtesla. And so we've done some preliminary work, built basically a structure. We have a Helmholtz coil for measuring these things, and we've done some measurements looking primarily in vacuum and also in under atmospheric pressure, simply to see the impact of squeeze film damping. I won't go into too much detail on that, except to note that the preliminary measurements, and this is just bringing a magnet close to across the small magnet. I'll give you some actual results next slide. So this is comparing ambient to vacuum. You can see the red is what I see in a atmospheric pressure ambient, and this peak is what I see when in vacuum, right? So because squeeze film damping is essentially what damps the response of the beam to the magnetic field. I should have mentioned that the current source used to supply the current through the film is an AC source, so you're basically sweeping frequency here and connecting with the resonant frequency of the mechanical structure. And whoop, yeah, okay, and this is actually in a normal optical in a magnetic field of 10 microtesla, and you can see the sort of response you get between what you see without any magnetic field, which is the and this is just based on the natural resonance of the mechanical structure compared to with the magnetic field. So everything works. We haven't yet set it up completely with a calibrated magnetic field to test the ultimate sensitivity, but we should basically have it all set up pretty soon. You can see some of the experimental setup there. I should mention that the device is effectively limited by Brownian motion in the cantilever. So I'll finish off by saying basically, it's a Lorentz force magnetometer that combines the sensitivity of an optical readout with the size, weight and power advantages of an integrated capacitor readout takes advantages of the two different approaches. And the next thing, by the way, those measurements are measuring it with a laser vibrometer. We haven't actually built one on top of a waveguide because the waveguide chips that we have are limited in number and extremely expensive because they were fabricated by a foundry. So we're waiting to get all of this done and then we'll build the cantilever. I think it's just been fabricated now and we're ready to measure it on the actual waveguide readout, luminance readout. Thank you.
Thank you, Laurie. Any questions? Yes.
Very interesting talk, thank you. I wonder, based on the Lorentz force nature of the device, do you have any problems if the magnetic field is parallel to the direction of the current or close?
Well, the idea is, if you want the vector, the actual direction of the magnetic field, then you would have one here, and one here, right? To cover the full three dimensions, otherwise just rotate the instrument.
So would you need the three of them?
Sorry?
Would you need the three sensors?
Well, yeah, to get the full vector, yes. That's what they need, a vector magnetometer.
Thank you.
Because in the end, you're just measuring the component in the direction of the current, right? Sorry, orthogonal to the direction of the current.
Of course, yes.
Because it is so sensitive, this cantilever, is temperature a big problem? When the temperature drifts, you get different reading?
I can't say that we really have done that in excruciating detail. This is at raw room temperature, right? That's the big advantage. It doesn't have to go down to low temperatures. If you cool it, it'll only get better. So you could probably, you'd probably temperature stabilize it with a tea cooler or something.
If it's an issue.
Yeah. But I've been assured that sitting on the ocean floor, the temperature doesn't change very much. And it's nice and really cold.
Okay, well, thank you very much, Laurie.
No, thanks.